let's see, what's the Fourier transform at 0? Well, if you write it again, let's use x as a random variable with so this is a random variable with distribution mu or law mu. So then we can write it as this way. And now when we ask the Fourier transform at 0, so then we plug in theta equals 0. So we put 0 times x, well, that's 0, so it's 1. It's the expectation of 1, which is 1. So the Fourier transform at 0 is always 1. That's one basic property. Second basic property is that mu at any theta in absolute value is at most 1. That comes from the Euler formula for sine and cosine, so we actually saw it already. Third property, mu is function from the real line to the complex plane, and it's not a bad function. It's a good function, meaning that it is a continuous function. It's a continuous function. Why is it continuous? Let's do a proof of this. Why is the Fourier transform of a measure, of a probability measure, a continuous function? So let's assume that we have a sequence theta which is converging to some theta in the real line. So then what can we say about mu Fourier transform theta n? When we use the same notation that x is this random variable, we have theta n x here, and we take the expectation of this. We ask, does this, what we want to do is to prove that actually this is converging to e theta x. Yeah. Is this true? Let's give this a name that we want to look. Let's give this a name z, and let's give this one a name. This is z and this is z. So now, because theta n is converging to theta pointwise, we also learned that zn is converging to z pointwise. I think that's clear. Can we use the Lebesgue dominated convergence theorem now to change the limit and the integral? So to do that, we would need to have an upper bound for z with some random variable x, or well, x is now used, but let's call it w, such that the expectation of the absolute value of w is finite. Well, w is non-negative, but so we could remove the absolute value. Can we find such a w which is dominating the zn's uniformly in n? What do you think? Is it possible? Well, it should be possible because I already stated as a fact that this theorem should be true. The answer is yes, you are correct. Because we know that this is e to the I to something with the real number, so it's every value here is it's in the complex unit disk. It's in the circle there. So actually that means that absolute value of zn is less than 1. So by noting this, we actually know that we can take as w, we can take w to be identical 1. And then of course the expectation of 1 is 1. That's a finite number. So we have this 1 here. We have the dominated thing here. So using these notions, we conclude that yes, this is true by the Lebesgue dominated convergence theorem. And that's the proof where we of the part C, that yes, the Fourier transform of every probability measure is a continuous function. It's quite remarkable. Let me also state that the Fourier transform is well defined for any probability measure. So it could be a probability, a discrete distribution. It could be a smooth Gaussian distribution. It could be something which has no mean even. It has no moments, infinite second moments, so fat tails that nothing converges. As long as it is a probability measure, it always has a Fourier transform well defined in every theta, and it is a continuous function even. No matter how kind of bad the original distribution is, the Fourier transform makes it continuous. So